We continue now.
I'm just going to wait 1 minute. There's like a million people walking in. Okay, thanks. Let me get started. So, one of the interesting things that ADS-CFT, or gauge gravity duality, has taught us is that black holes are pretty much ordinary quantum mechanical systems. And in many cases, we know the specific quantum mechanical system involved. However, this hasn't been maybe quite as helpful for understanding quantum gravity or the physics of black holes as you might have thought. And one of the reasons is that the quantum mechanical systems that are involved are very strongly interacting, involve many degrees of freedom. They're difficult to analyze directly. So one approach for extracting some information from this fact is to use very general properties that are obviously true for any quantum mechanical system and see how those can be true for the black hole. So a very famous example of this is just the fact that any quantum mechanical system, no matter how complicated, has unitary time evolution. And this basically gives a one-line proof that black holes in string theory don't destroy information. So this is something important that we learned from this, maybe we learned in the most precise way from this fact. So today we're going to discuss something which is maybe a little bit in this direction, which is another very universal feature of interacting quantum mechanical systems. This feature has to do with the statistics of the energy eigenvalues. And let me just illustrate what we're going to be talking about. Let's imagine that we have some quantum mechanical system with many degrees of freedom, so it has a lot of energy eigenvalues. And let me plot a plot of the coarse-grained density of states. It looks something like that. And if we zoom in on some small region of the spectrum, then if we're studying a quantum field theory in finite volume or a quantum mechanical system, then a system like that will have a discrete spectrum of energy levels. So this thing will be resolved, and we'll find a bunch of delta functions at some values that correspond to the actual discrete set of energies of the system. Now, what we'll be discussing today will have to do with the statistics of these numbers, these eigenvalues. And your first guess, if we have a somewhat complicated system, is that these should be roughly random numbers. And one thing that you might mean by that is you take an interval in energy. I'm going to draw it vertically this time instead of horizontally. And you just throw darts at the interval. So you pick uniformly distributed random numbers. Those will give a set of energy levels that might look something like this. The statistics that corresponds to this is known as Poisson statistics. And these statistics actually describe accurately the spectrum of energy eigenvalues for very special systems, where, for example, the Hamiltonian is a sum of a whole bunch of commuting terms. And in those cases, the spectrum of energies does indeed have the statistics like this, just uniformly distributed in some interval. But that's not what you find if you study the eigenvalues of a interesting interacting quantum mechanical system. So this one is Poisson. What you find if you study the eigenvalues of an interacting system is something that looks more like this. The levels are distributed in a much the levels are distributed much more regularly. And in particular, it's quite rare to find configurations where there are a pair of energy levels that are very close together. So you could ask, what is this? What is the actual statistics of these energy levels? And the conjecture is that these energy levels are distributed like the eigenvalues of a random matrix. This conjecture is known as random matrix universality, and it has a very long history in physics. I guess going back to the work of Wigner, maybe earlier, I'm not sure. But it's been studied very intensively in, well, a few different areas in physics, including in some areas of condensed matter physics, and in many body theory. There's a whole subfield of physics called quantum chaos, or semi-classical quantum chaos, where they study this type of problem for classical systems that you quantize. And they study the energy eigenvalues of those systems and try to prove that they have random matrix statistics. It hasn't been studied very much, well, it hasn't been studied as much in our subfield. But I want to emphasize that the conjecture, the random matrix universality conjecture, is like extremely general. The claim is that you should have this statistics for basically any interacting quantum theory. There's a couple of subtleties there. One subtlety is that you should have this statistics only within a particular block of the Hamiltonian, where corresponding to a given value of whatever global symmetry charges you have. Another subtlety is that actually there are a few different ensembles of random matrices, and they'll have slightly different, well, there are many ensembles of random matrices, but from the perspective of these fine-grained statistics, there are a few different ensembles. And those ones depend, for example, they depend on very primitive features of the theory, like time reversal and variance properties, fermion parity properties. But once you've identified those, then if you take almost any interacting quantum mechanical theory, it could be like the 3D Ising model on a sphere. It could be n equals 4 super Yang-Mills theory. It could be a particle bouncing around in some irregularly shaped stadium. It could be the SYK model. And you zoom in on some region of the spectrum. The claim is that you'll find these statistics. Now, so this is a property which is sort of general enough that it should be true for black holes as well. And what we would like to do is understand how black holes manage to exhibit this property of generic property of quantum mechanical theories. Now, what we're going to do in the lecture today is we're going to explore this, some aspects of the statistics just in random matrix theory, but also in the SYK model. The SYK model is a sort of useful stepping stone between random matrix ensembles and gravity. That's because, as we've discussed, there are different ways of analyzing the SYK model. One is just actually by constructing the matrix on your computer and diagonalizing it. And then you can find all the eigenvalues and you can check this, and it's true. But there's another way of analyzing it using these collective fields, and that's a little bit like a gravity theory, where the Hilbert space is not manifest. And actually, as we saw, at low energies, the SYK model contains within it this theory of two-dimensional gravity. So SYK is sort of a useful stepping stone for analyzing this problem. Yeah. Why they should be more spread out than this? Yeah, we'll see that in a second. Yeah. Mm-hmm. Okay, so, but it will be helpful to have in mind some kind of observable that we can compute. Why is this happening today? I don't know. Thank you. Well, I'm afraid that will be too close. We'll see. It will be helpful to have in mind a particular observable to compute that will be sensitive to the statistics of the energy eigenvalues. Because most of the things that we calculate in physics are not. Like the coarse-grained thermodynamics, simple correlation functions, these things don't care about the energy eigenvalues. This is some extremely fine-grained thing that gets smeared out when you calculate an ordinary quantity in a physical system. So we have to study something a little bit unusual to be sensitive to these to the difference in the first place. So an example of a thing you can compute, this has been studied in the random matrix theory community for decades, is the spectral form factor, is what it's called. We'll study something which is closely related to that, and we'll refer to it as the spectral form factor. So the function z of beta is the thermal partition function. It's the trace of e to the minus beta h. And here we're just continuing it in its argument beta. So this thing can be written as a double sum over the spectrum of energy eigenvalues of the theory, e to the minus okay. And actually what we'll be interested in is the average of this quantity over the ensemble, over an ensemble of matrices. So in random matrix theory, you can just draw multiple random matrices from your ensemble. And in the SYK model, you can draw random multiple instances of the SYK Hamiltonian with their own respective random J couplings. So we'll be interested in the disorder average, either the average over J or over the random matrix ensemble of this quantity. Okay, so I'll draw a plot for you of this thing now. And, well, the plot is basically the same in the SYK model and for a simple random matrix ensemble, so I'll only draw one plot. But just to say what I'll be plotting, the random matrix ensemble that we'll begin by considering is one, it's called the GUE ensemble. It corresponds to just taking all of the different elements of the matrix to be independent random Gaussian distributed numbers up to the constraint that the matrix should be Hermitian. And we'll consider a matrix that's L by L. And L should be compared in the SYK case to 2 to the n over 2, the rank of the Hamiltonian. So the plot looks something like this. We'll do a log-log plot. So this is the logarithm of t. And this thing will be the log, y-axis is the log of this quantity. And it looks something like this. Okay, and I'll draw a couple of values here. It starts out at t equals 0. It starts out with a value that's of order L squared, because it's a sum over, a double sum over the spectrum of the eigenvalues, so there are L squared terms. So it starts out with a large value, order L squared. At very late times, it has a value where basically only the diagonal terms in this double sum contribute, because at late times, the off-diagonal terms will be oscillating and will cancel out. So at very late times, we have only the diagonal terms, so there are L diagonal terms in this double sum. So the late time value is proportional to L. And in between, it has this interesting time dependence, where there's a region here that's sometimes referred to as the slope, where the function looks like L squared over t cubed. And there's a linearly increasing region here, which is sometimes called the ramp, where the function is basically linear in time t with a coefficient that's not proportional to L, just an order 1 coefficient. Yeah, it's this region. So, and this region here where it's of order L we'll sometimes refer to as the plateau. You can figure out what times the crossovers between these three different behaviors are just by setting them equal to each other. Yes? Sorry?
What's the subsquared over there? Is it like,
What is this?
yeah, is that squared? Z-squared.
Yeah, z squared is this thing. That's this. Yeah, I just didn't want to write out all the arguments, beta plus it and beta minus it. Yeah, I will do that a little bit. But if you feel unsatisfied in like 15 minutes or something, ask me again. Whoa. I don't know what just happened. There were two people that talked. I don't know who they were. Okay.
What was behind this graph? There's no dependence on it. You just keep it fixed and vary.
Yeah. Let's keep beta fixed.
And if you fix it at some other value, you'll get exactly the same.
No, you'll get a somewhat different curve, and actually
But similarly looking.
similar looking. Yes. And the value here, well, in SYK, it won't be exactly L. It might be a power of L that's slightly different than this. But I'm going to suppress that subtlety for now. It's not a interesting subtlety. There was another comment or question. Yeah.
Is it linear in T or linear in non?
It's linear in T. Yeah. Okay. This is a log-log plot. So any power would have been a line, but this is a special line, and this one is also linear on an ordinary plot, not just a log-log plot.
Doesn't z squared go like L squared?
This z squared initially is like L squared.
Yeah, but you wrote log.
Oh, okay. You're right. What I'm drawing here is the value of z squared, not its log. Yeah. Okay, so you can figure out where the times are, where these behaviors intersect. For example, this here, where the ramp meets the plateau, will be a time of order L, because it's growing linearly like t here, and it's constant L there. So this is a time t of order L. So L is the number of eigenvalues, so it's 1 over the eigenvalue spacing. So this time here is the Heisenberg time that was discussed by Jose in his lecture yesterday. The intersection here between the slope and the ramp is less interesting, but you can work out that it's t of order square root of L from setting these two expressions equal to each other. Okay. Sorry, how do you define it? You just this roughly flat part of the curve here.
So it's not the constant for
Yeah, it's approximately constant in this region. That's why it's referred to as the plateau. Okay. Well, I was asked what is the physical interpretation of this quantity? And actually, I'm not sure I'm going to give a very good answer for that. It's not a particularly physical quantity. But what it does do is it exposes the statistics of these energy eigenvalues. And we're going to see that these features of the plot, the slope, the ramp, and the plateau, are related to different aspects of the statistics of the energy eigenvalues. And there's another answer to this question, which is the following. If we think about a two-point function in the thermal ensemble between an operator at time 0 and an operator at time t, then that has an expression as a double sum over the energy eigenvalues with phase factors that are similar to these. For a particular arrangement of a two-point function, we have a beta over 2 here and a beta over 2 there. It also has some matrix elements squared of the operator between the energy eigenstates. Now, if you believe that the matrix elements squared don't vary in a very interesting way as a function of the energy, then you might think that this would be a reasonable approximation to the two-point function. And at late times, I think that's true. So that's a more physical quantity that's somewhat related to this one. Yeah, that's right. That's right. So you could appeal to the ETH or eigenstate thermalization hypothesis to say that you think that the squares of these matrix elements of the local operators between different energy eigenstates are basically the same, or they're random quantities. But yeah. Yes.
They're really nearby.
Well, they're the ones that are interesting for the late time are fairly nearby. Yes. Yeah.
Can you say what qualitatively this plot would have looked like if there was Poisson distribution?
Well, yeah. One feature is that we won't have this ramp. We won't have the ramp at all. And I think the type of thing you can have is just the curve can just decrease and plateau without having this ramp region. Okay. So our goal today will be to try to understand as much of this curve as we can in both. Oh, sorry. I should have said where this comes from. This comes from just doing exact diagonalization of the SYK model, or you can do exact diagonalization of the random matrices. In the random matrix theory case, you can actually compute this curve analytically, which we'll basically do. But you can also do it numerically if you want. And you just can compute this curve on the computer. So our goal is to try to explain analytically in the SYK model as much of this curve as we can, and ultimately in a black hole as much of the curve as we can. And we'll study this in JT gravity today. And we're first going to start by understanding where this curve comes from just in random matrix theory. So let me define a random matrix ensemble. So the big random matrix partition function is given by an integral over matrices of e to the minus L, the rank of the matrix, times the trace of some potential function of the matrix. So for example, for the Gaussian unitary ensemble, the case that we just discussed, this function will be m squared over 2. This is the GUE case. And this is actually a case that we'll focus on a little bit later. But you can put some arbitrary function here. Now, we're interested not just in the in properties of the matrix as a whole. We're interested in the properties of the eigenvalues. And so from that perspective, it's useful to think about m going to u dagger as a gauge transformation, so that only the eigenvalues are gauge invariant quantities. And we can get a integral. We can represent this integral just in terms of an integral over the eigenvalues. So in other words, we can understand the probability distribution for the eigenvalues by doing the Fourier-Popov procedure to gauge fix this integral. So that's based on the following. So let me define little h to be a small gauge transformation, which is going to act on m by e to the ih m e to the minus ih, which is approximately m plus I times the commutator of h with m. And for the Fourier-Popov procedure, we would like to start with a diagonal matrix M. So M equals a sum over A of some eigenvalues A times projectors onto the 8th eigenvector. And then we'd like to make a small variation with a gauge transformation and compute the determinant of the off-diagonal elements with respect to this small gauge transformation. So that's convenient. It's convenient to use the following to say that if we take H to be some off-diagonal matrix element, off-diagonal matrix like this, then we have H commutator with M, where I'm using this expression for M, is equal to lambda D minus lambda C times H. So that means that this little h here is an eigenvector of the operator dm AB dHCD, an eigenvector with this eigenvalue, lambda D minus lambda C. And the determinant we want, the Fourier-Popov determinant, is just this determinant. So we'll take a product of these eigenvalues over all of the pairs C and D. And you need to take a product of two such factors for the gauge fixing of the real and imaginary parts of the off-diagonal matrix elements. So this determinant is product over A less than D, lambda A minus lambda B squared. So this is our Fourier-Popov determinant. And what it means is that the probability distribution for the eigenvalues is this factor times the term that we get just from here. Okay, so this is step one of the analysis. This product factor out front is called the square of the vandermonde determinant, and we'll see why it's referred to as a determinant in a moment. Now, for large values of L, this probability distribution for the eigenvalues is sharply peaked. Naively, it is a probability distribution that wants all the eigenvalues to be sitting at the minimum of this potential. But you can see that this factor here vanishes if two eigenvalues coincide with each other. That actually explains the fact that the probability distribution for these eigenvalues preferred configurations where they were more evenly spaced. If eigenvalues are close to each other, this factor vanishes, so the probability is small. But if all the eigenvalues are on top of each other, this factor will complain. So there's some kind of a compromise which is reached between the repulsion due to this vandermonde determinant and the fact that the eigenvalues want to be sitting near a minimum of the potential. And we can use that to solve for the distribution of eigenvalues you have at large L. So one way to do that is to use basically a mean field analysis and compute the effective potential that a single eigenvalue feels. So the effective potential for some eigenvalue, let's say eigenvalue A, is L times the bare potential, just this function V of lambda A, minus a term coming from the sum over all these other eigenvalues. Sum over B not equal to A log lambda A minus lambda B squared. Now, in order to solve for the distribution of eigenvalues at large L, we're going to introduce a function rho naught of lambda. That's the limit as L goes to infinity of the probability distribution for just a single eigenvalue. And in terms of this function, we can write this sum at large L as an integral d lambda prime of log of lambda A minus lambda prime squared times rho naught of lambda prime. Okay? Now, the equilibrium condition for the eigenvalues is that this effective potential should be stationary with respect to variations of this eigenvalue. There should be no net force on an eigenvalue. There's some force from the potential, and then some additional force from the effect of all the other eigenvalues. And the condition for the equilibrium density is that those two effects should cancel. So that implies that V prime of lambda A is equal to 2 times integral d lambda prime okay. So this equation actually determines this equilibrium density of eigenvalues at rho naught, which is the large L probability distribution for a single eigenvalue. This equation is a little bit awkward, but by manipulating it, and you can get an explicit equation for rho naught in terms of the potential. This is an implicit equation. I'm not going to go through that in detail, but just as an example, for this case, for the GUE case, where we take the potential to be m squared over 2, one finds this expression. Rho naught of lambda is 1 over 2 pi square root of 4 minus lambda squared. So this is sometimes referred to as the Wigner semicircle. It's a distribution that's supported between -2 and 2, and it's a semicircle. So this is the equilibrium configuration of the eigenvalues at large L. But what we need is more than this, because the z times z star quantity, the spectral form factor, is a 2 eigenvalue quantity. It involves 2 copies of the partition function. It's a double sum over eigenvalues. So to compute it, we'll need not just the probability distribution for a single eigenvalue, we'll need the joint probability distribution for a pair of eigenvalues. And we'll actually, in order to get the whole curve, we'll need to know this function in a fairly good level of precision. And that's not an extremely easy calculation. It's not terribly hard, but it's not extremely easy. And there are many different methods for doing it. And the one that I'm going to show you is, in some sense, it's sort of like a heavy hammer, which can be employed in the discussion of random matrices. It's not very convenient for thinking about SYK or gravity, but I wanted to show it to you as a very useful tool in the analysis of random matrices. It's known as the method of orthogonal polynomials. And so the discussion is going to get a little bit dry for a little while. And, well, I'm not going to apologize for that. It's just sort of the nature of this calculation. So the basic thing we'd like to do is take this probability distribution for the eigenvalues that we had, involving the vandermonde determinant and the expression from the potential, and somehow marginalize it over L minus 2 of the eigenvalues to compute just the probability distribution for a pair of eigenvalues, and then analyze that one in some practical way. A useful first step in doing this is to use the following. So we can write this vandermonde determinant. So this expression here is sometimes referred to as vandermonde determinant, delta of the collection of eigenvalues. We can write this as a determinant of the following matrix. So in the first column, we have just all of the eigenvalues of the matrix. In the second column, we have the eigenvalues squared. In the third column, we have the eigenvalues cubed, and so on. It's sort of a fun exercise to show that this is the case. You can use the fact that it's a totally antisymmetric polynomial with the right degree, and that vanishes when eigenvalues coincide with each other. Sorry? Sorry. We should include a 1 column as well. So it's useful to write an alternate expression for this determinant by doing column operations on this matrix that don't change the determinant. By doing column operations, we can have polynomials of the eigenvalues here, monic polynomials of the eigenvalues, with degree 1, a polynomial of degree 2, polynomial of degree 3, and so on. And this manipulation, the fact that these determinants are equal, is true for any collection of monic polynomials. Yeah, is that not what monic means? I could be wrong about that, but yeah, the important thing is that the coefficient of the highest power is 1, and well, we won't actually worry too much about the normalization of the probability distribution, so even that fact won't be too important. But we can write this vandermonde determinant as a determinant of these polynomials. And it's very convenient to choose a particular choice of these polynomials. We'll choose the polynomials to be the ones that are orthogonal with respect to the measure e to the minus L p of lambda, Pn of lambda. We'll choose them so that this thing is proportional to delta nm. Okay. So the point of doing this is the following. We can write the full probability distribution now. So the full probability distribution of the eigenvalues is this vandermonde determinant squared times the factor e to the minus L times the sum over n v of lambda n. We can write this thing in the following way as determinant of, I'll explain why this is true in a second. So this is a determinant over I and j. The I and j indices are running from 1 to L. And let me define this function psi. So the function psi m of lambda is our polynomial times e to the minus L v of lambda over 2. And where does this expression come from? Well, the vandermonde determinant squared we could write as the determinant of the product of two factors of this matrix that we had. And actually, it's convenient to write it as the determinant of the product of the matrix times the transpose of that matrix. And the elements of the matrix times the transpose of that matrix are this expression here with p's instead of psi's. And then if we just want to include this factor, the factor of e to the minus L v of lambda, in a determinant instead of adding it on at the end, then we multiply those functions p by this factor. And the whole thing reduces to this expression. Okay. So this was some sort of complicated procedure that we did. Now, the nice thing about this is that it makes it easy to integrate out some of the eigenvalues. Because, well, whether this is helpful or not depends a little bit on your background. But this thing here is the probability distribution for a Slater determinant wave function for fermions in the lowest L levels of the quantum mechanics problem with this potential. So the Slater determinant for is a wave function for identical fermions where you antisymmetrize over which of the fermions you put in which of some collection of energy levels. And this probability distribution is the square of that Slater determinant wave function. And something that you can check, it's not hard to check, is that if we want to calculate the probability distribution for just a subset of the eigenvalues, lambda 1 up to lambda k, then that's proportional to the determinant of k, lambda I, lambda j, where now I and j are running from 1 up to k. And this kernel here, k, is just the sum of these psi functions. Okay. So this is a very powerful formula. It gives you the probability distribution for any subset of k of the eigenvalues. What we want is we want a probability distribution for just a pair of the eigenvalues. So that will be a determinant of a 2x2 matrix built out of this kernel k. So to complete our analysis, we just need to compute this kernel, k of lambda and lambda prime. Okay, this part involving the determinants is actually the maximally dry part of the calculation. The part involving the kernel is a little bit more fun. So we can think of this kernel. Now, from now on, I'm going to specialize to the case where this potential is, where the potential is lambda squared over 2. So now these polynomials are the Hermite polynomials. And the psi functions here are the wave functions of the harmonic oscillator. So the psi function with subscript m is the mth wave function of the harmonic oscillator. So this kernel is just a projection operator onto the first L eigenstates of the harmonic oscillator. And we can write what that means as a differential operator. So we want to write the differential operator for the Hamiltonian of the harmonic oscillator, and we want to say that its eigenvalue is going to be less than or equal to L. So let's write that out. There's some factors of L that are sort of not standard because the potential was L times lambda squared over 2. And what that gives us is the following harmonic oscillator Hamiltonian. So we want the eigenvalue of this operator to be less than or equal to the Lth energy level of the harmonic oscillator, which is L plus a half. Okay, so we want to write an operator that implements that condition. And that will be the operator K. Now, to get an actual expression, doing this exactly is hard. But what we can do is we can do it when the eigenvalues lambda and lambda prime are close to each other, somewhere in the semicircle, and L is large. So we can say that lambda is equal to some lambda naught, the center of this point, plus a parameter we'll call x, divided by L times rho naught of lambda naught. This is a convenient normalization factor. And the factor of L here means that we're going to be close to this eigenvalue lambda naught. Similarly, lambda prime will be lambda naught plus x prime over the same normalization factor. Okay, now we'd like to rewrite this differential operator in terms of the x variable instead of the lambda variable. So that rescales this term here. And we're also going to approximate lambda in this factor by lambda naught. So we get minus L is less than or equal to L plus a half, but we're going to take L large so we can drop the plus a half. So we have this condition. And now let's write this out. This is minus, well, we can cancel the factor of L from all of the terms. This factor, rho naught, if you remember the expression we wrote before for the leading density of eigenvalues, rho naught, that was this semicircle function. And if we square it, we get this. Okay, and now if we just divide by this factor, we find a very simple condition that minus dx squared is less than or equal to pi squared. And it's easy for us to write a differential, an operator that implements this condition. The operator that implements this condition would be, so this will be our operator K, and K in terms of x and x prime will be the x matrix element of dk minus pi to pi k k x prime. This is okay, so this is the answer for the kernel. in this limit. This is a very famous expression. This expression here is called the Dyson sign kernel. And we derived it here for the case where the potential is just lambda squared over 2, this GUE case. But you get the same expression for any potential as long as you're looking at small separations between the eigenvalues. You can do that, and as long as you're not near the edge. Even in the Gaussian case, the kernel is different near the edge. So if the pairs of eigenvalues are very close to the edge, there's a different expression involving the Airy function. That one's called the Airy kernel. But in the bulk of the spectrum, if the eigenvalues are close to each other, then for any potential, we get this sign kernel expression with some rescaling of the x variables. Yeah. We used that here. So we wrote lambda was lambda naught plus x over L. And we were imagining that x was fixed and L is large. So so this is small and this is small. So lambda and lambda prime are close together. Okay, so let's now compute the probability distribution for a pair. We need to compute the determinant of a matrix that looks like, so probability distribution for a pair, x prime, is the determinant of this matrix, k of x, k of x prime, k of x prime x, k of x prime. And that determinant is 1 minus sine squared pi x minus x prime, or pi squared x minus x prime squared. So let's plot this function. Let's say that one of the eigenvalues, let's say x, is a point 0, and we'll plot this function as a function of x prime. It starts out at 0, and it is quadratic, and looks something like that. So it's 0 because there's 0 probability for the eigenvalues to be coincident, and the probability is quadratic for small separations. This function has two features that will be important. They'll be reflected in the spectral form factor. One is the oscillations in x. These oscillations here, you can kind of think in the back of your mind that what this distribution wants is it wants like our first eigenvalue to be here. It wants another eigenvalue there, another eigenvalue there, and so on. So there are these oscillations in x. In terms of the lambda coordinate, which is x over L, these will be very rapid oscillations, like sine squared of L times lambda. The other feature of this thing is it has this envelope. We could draw some envelope function here. And the envelope function is like 1 over x squared. So there's slightly higher probability for the second eigenvalue to be far away from the first eigenvalue. And that's small change of the probability is decaying only as a power. So this is a very long-range effect. This effect is known as the spectral rigidity. And it's a sort of surprising feature of these eigenvalues, that they have a very long-range power law repulsive anti-correlation with each other. So yeah, it's a descendant of the repulsion in the vandermonde determinant, but it's sort of an interesting fact that we get this power law. And these two effects, the oscillation will be related to the plateau in the spectral form factor, and the power law here, the spectral rigidity, will be related to the linear ramp. So I'll try to make that a little bit more clear. So what we want to do first is an easy thing, which is to write this probability distribution in terms of lambda instead of in terms of these x's. So that looks like the following: p of lambda and lambda prime. Keeping track of the fact that the probability transforms like a density, we get rho naught of lambda rho naught of lambda prime. That's this one term minus sine squared pi L rho naught of lambda naught times lambda minus lambda prime over pi squared times L squared times lambda minus lambda prime. Okay. Now we'd like to use that expression to compute the spectral form factor. So the spectral form factor, the average of the spectral form factor, z beta plus it, z of beta minus it, in this random matrix ensemble is the following expression in terms of the probability distribution for the eigenvalues. So it's L squared times the integral d lambda prime times this probability for the pair times the factor e to the minus lambda beta plus it minus lambda prime beta minus it. Well, there's also there's a second term. This is the obvious term. The second term expresses the possibility that the two eigenvalues in the double sum could have been the same. So this term takes track of the case where the two eigenvalues in the double sum were different, but we have to also include the term where the two eigenvalues were the same. That only comes with a factor of L instead of L squared because it's just a diagonal term. And we get this expression. Okay. So if you take this expression and plug it in here and do the integrals, you find the slope, the ramp, and the plateau. So I'm not going to do the integrals for you right now. It's actually kind of entertaining to do basically what one needs to do is the Fourier transform of this sine kernel expression. And the Fourier transform of this function, sine squared x over x squared, is like a tent function. It's a triangle. And that triangle gets inverted because of the minus sign, and it gets offset. And that triangle becomes the ramp function ending in a plateau.
So the plateau is the last term.
Yeah, the plateau comes from this term. That's right. But let me try to explain just qualitatively the three different regions of this function. I didn't draw this very well. So the plateau, as we just said, comes from this last term here, the term where both eigenvalues are the same. The ramp, the ramp and the plateau both can be understood coming from the Fourier transform of this term plus this. But the ramp in particular has a simpler origin. You don't need to include this sine squared factor, this oscillating sine squared factor. You can just do the integral replacing sine squared of the difference of the eigenvalues by its average value, which is a half. And then in this integral, one is essentially computing the Fourier transform of 1 over x squared. And that's a function that is growing linearly. The Fourier transform of 1 over x squared is k. In this case, the Fourier variable is time. It's not k. So we get a linear growth from that 1 over x squared. So that's the sense in which the spectral rigidity leads to the ramp. This power law repulsive anticorrelation of the eigenvalues leads to a linear ramp. And this sharp feature, sorry?
You don't have slight oscillations. Is it exactly linear or
It's so it's exactly linear from this function. The effect of the sine is to give a sharp feature at this point. So in Fourier space, so the time axis here is like Fourier space, and the sine is a thing which is oscillating. We're going to write sine squared as like a constant plus a cosine. So it has a constant piece plus a term that's oscillating a very specific frequency. So that very specific frequency shows up as a sharp feature in the Fourier transform. That sharp feature is this kink here, where the ramp turns into the plateau.
so that's really sharp.
Yeah, that's sharp with this function. But what we have here, in this distribution, the argument of the sine squared is modulated a little bit by the location of the center of the pair of eigenvalues. So really what you have is a sum of a bunch of these sharp ramps with slightly different points where they take place. So actually in this ensemble, that feature gets smoothed out a little bit. And it gets smoothed out even more in the SYK model.
In the same vein, is there an upper bound you can put for the plateau, or are there oscillations around the plateau?
No, in this sense,
Can you declare an upper bound?
I'm not sure what you mean by an upper bound.
That it will never be larger than a certain number.
Oh, well, yeah. In this case, it's really just a constant at large time, and it's a constant forever.
So
It never comes back up. That's because we're taking this is the ensemble average. So maybe you have in mind some kind of recurrence effect, but the recurrence doesn't take place in the ensemble average. A recurrence phenomenon could take place for a given matrix, but it won't take place in the ensemble average. Yeah.
Can you comment about self-averaging?
Yeah, I will comment on that, but not right this second. There's another comment I want to make first, which is to explain the slope, the initial decrease here. So that one is explained just by the first term in this probability distribution, the factorized term. So if you look at this expression, you'll notice that the first term is much bigger than the second one because of this factor of 1 over L squared. So this term is of order 1, this term is of order 1 over L squared. L is big, we have a big matrix, this is a small correction to the first term. So for most purposes, the probability distribution just factorizes into a product of the individual probability distributions for the two eigenvalues. And that's enough to explain this slope region. The particular power that we get, so we get L squared over T cubed. The power 1 over T cubed comes from integrating near the edge of the probability distribution rho naught of lambda. So let me just comment on that briefly. So if we compute z of beta plus it by doing an integral d lambda rho naught of lambda e to the minus beta, sorry. This expression here, rho naught is a function that looks like that. Then for large t, we're computing, again, the Fourier transform with large argument of this semicircle distribution here. And the Fourier transform of that function with large argument is determined by the region of the function where it varies most rapidly. And it varies most rapidly at the edge of the semicircle. So at large times, we can get away with just doing the integral very close to the edge. Near the edge, it vanishes like a square root. So we have an integral that looks like, well, I'm running out of space there, so let me write it up here. We have an integral that looks like, I'll use x instead of lambda, x times square root of x from 0 to some upper limit of e to the minus beta times e to the minus x times beta plus it. And this integral is proportional to 1 over beta plus it to the 3 halves. So for large t, it's like 1 over t to the 3 halves. In z times z star, we have two factors of this expression. So we have power law behavior 1 over t cubed. That 1 over t cubed, we've just explained as arising from the square root of energy edge in the probability distribution for the energy eigenvalues. Okay, so that's the end of the discussion of these three parts of the curve in random matrix theory. Now, I was asked a question about the self-averaging property of this curve, and that's an important thing to discuss. So before we move on to SYK, let me comment on that. So before I plotted for you the ensemble average of the spectral form factor. This curve here. But we can also ask, what if you just take a single random matrix and you plot this z times z star for just one matrix, not for the ensemble average of z star, just for a particular matrix, z times z star. Then in the slope region, it looks basically the same. that follows from the fact that in the slope region, we were really just sensitive to the single eigenvalue probability distribution. We could use a factorized expression for the pair correlation function. But after that point, the correlations in the pair correlation function were important. And it will be quite different. And actually what the curve looks like after this point is it stops self-averaging altogether and it becomes some kind of very erratic function that has a time average or an ensemble average that's given by the smooth ramp and plateau. And actually the level, I want to emphasize that the level of erraticness is really quite extreme. And it's beyond my artistic ability to convey. But really the function like fills out this whole space.
I mean, these are of order L, L squared.
The oscillations are on a time scale, which is the inverse of the. Oh no, the oscillations are of order the mean. So the fluctuations are the same size as the average, but they're on a short time scale. So they're, the x-axis here is like an exponentially long time. So there will be many, many oscillations. So it will be filling up something like that.
Oscillation come from simulation?
From what?
Come from simulation?
Well, yeah, it comes from taking one matrix and then plotting the function for that one matrix instead of for the ensemble average. Yes? Could you speak up, please? Well, it's an approximation of it, yes. Sort of, yes, sort of. Yes.
What is the reason that this connected part at large times is only getting contribution from the bulk of the spectrum and not near the edges?
Ah, yeah, that's because okay, we can discuss that both for the slope and the ramp. The late time feature in the ramp region is determined by a singularity in the pair correlation function when the eigenvalues approach each other. There's a large value here when the eigenvalues approach each other. And that's true if the eigenvalues are close together in the bulk or near the edge. And most of the eigenvalues are in the bulk. So the most important contribution comes from the bulk of the spectrum. That's different from this computation, where the singularity that was important for the long time behavior was only present at the edge. So in the non-self-averaging part, in this part and this part, all the eigenvalues contribute to, most of it comes from the bulk.
You were about to give an expression for the spacing in time. Can you just say what it was? What order of magnitude is there?
Yeah, the time scale is the inverse of the typical energy separation in the ensemble. Okay, so now we're going to move on to trying to understand as much of this curve as we can in the SYK model. And actually what we're going to do is, it can be done in the SYK model itself, but what we're going to do to make things a little simpler is study this in the SYK model at low energies, low temperatures, so we can use the JT gravity, where the equations are just a bunch simpler than in SYK. And also the connection to black hole physics is more obvious. So an important feature in this discussion will be the fact that the path integral of the Schwarzian theory, which is also the path integral of the JT theory, as we've discussed, is a one-loop exact path integral. And one-loop exact integrals are sort of miraculous. And so I'm not going to show in detail that the Schwarzian theory is one-loop exact, but let me show you an example of a one-loop exact integral so you can kind of see what it's about. Yes?
So we understood this Hermitian matrix model described in philosophy of maths. So what is the property here? Which kind of property will in philosophy of maths
Well, I think that's a very different. Yeah, that's not the Hamiltonian of n equals 4 Superior-Mills. That's a computation that arises in the computation of some special Wilson loops in the n equals 4 Superior-Mills. And I'm not sure of an interpretation of this physics in that context. It's an interesting question. Okay, so for an example of a one-loop exact integral, consider the following. We're going to do an integral over a sphere of the function e to the minus n times cosine theta. Okay. Now, how do you do this integral? Well, the d phi integral decouples. That gives a factor of 2 pi. And then you change variables to z equals cosine theta. D theta sine theta is dz. And we do an integral dz e to the minus nz. And we get the expression 4 pi sinh of n over n. Okay, so this integral was totally trivial to do exactly. But let's think about it for a second, and let's think about it as an integral when n is large. Then there are two saddle points for this integral. There's a saddle point when cos prime theta equals 0. So there's one at the north pole of the sphere at theta equals 0, and one at the south pole at theta equals pi. And let's just imagine that we're not going to try to evaluate the integral exactly, although it's trivial to do so. Let's evaluate the integral using the saddle point approximation. We'll evaluate the saddle point and the one-loop fluctuation. So that means that we have two contributions. I'll analyze just the one from the north pole, but you can do the south pole one the same way. We'll look at a contribution from the integral when theta is small. So we would write of this we would say this integral is approximately equal to an integral where theta is small. Well, we do d theta of a 2 pi from the phi. And then we approximate sine theta as theta plus higher order terms, which will be negligible if n is small. And then we do the same thing in the exponential. E to the minus n times 1 minus theta squared over 2 plus higher order terms that will be negligible if n is small. And we do just this integral, d theta theta, e to the minus n squared times 1 minus theta squared over 2. We add the contribution from the north pole saddle point and the south pole saddle point, and we get exactly this function. So this sort of approximate evaluation at large n gives us the exact answer. This is what it means for an integral to be one loop exact. Now in this case, it's super easy to just show that it's true by doing the integral exactly. But there are cases where that's not true. And it's helpful to have a general family of integrals that are one loop exact. And this is an example of the general family. So what is the general family? It corresponds to integrals over some symplectic manifold of, with the symplectic measure, so sometimes that's written as e to the omega, where omega is a symplectic form, of n times some Hamiltonian, where the Hamiltonian is a symplectic generator of a U1 symmetry of the symplectic manifold. So there's a theorem, the Dorster-Matt-Heckman theorem, that says the integrals of this type are one loop exact, thought of as a function of n. So how is that relevant in this case? The two-sphere that we were integrating over is a symplectic manifold, and the measure we're using here is just the symplectic form. This function cosine theta here, thought of as a Hamiltonian for that symplectic form, generates rotations of the sphere, holding fixed the north and south poles. So that's a U1 symmetry of the sphere. So indeed, this problem fits into this general class. And this would be the world's most complicated way to prove that this integral has that answer. The proof of this Dorster-Matt-Heckman theorem is actually, there's a simple way of proving it using supersymmetric localization. So now, why is that relevant? So we're going to be wanting to calculate the Schwarzian path integral exactly. And that's an integral of d phi over this space we've discussed many times, def S1 left quotient by SL2R of the expression to n S naught plus alpha n over j Okay, so this is the Schwarzian path integral. This is z of beta for the Schwarzian theory. And it just so happens that this manifold, diff S1 mod SL2R, is a symplectic manifold. And with respect to the symplectic form of that manifold, the Schwarzian action is a Hamiltonian that generates a U1 symmetry of the symplectic manifold. the U1 symmetry that it generates is corresponds to phi of tau goes to phi of tau plus epsilon. So that means, how do you see this? Well, you write the symplectic form, and then you check that this Hamiltonian generates the yeah, I couldn't write that. So the symplectic form depends on a small variation and the point that we start with. So I'm not going to have the factors right in this expression, but so let's say that we start at a point phi naught, and we consider a small variation delta phi. So the symplectic form looks like an integral d tau of delta phi double prime wedge delta phi prime. Then it's plus or minus, I'm not sure, the Schwarzian derivative of tangent phi over 2 with respect to tau times delta phi prime wedge delta phi. And it's straightforward. I'm not going to do it now, but it's straightforward to show that this symplectic form and this Hamiltonian generate this. How do we get the symplectic measure from JT gravity? Okay, the simplest way is the following. You think of JT gravity as a topological BF theory. There's a way of writing the JT gravity action in the first order formalism for gravity as a BF gauge theory, SL2R BF gauge theory. And the SL2R BF gauge theory, the B term, we do the integral, and it reduces us to flat connections. It sets F equals 0. This is a standard way of analyzing these BF theories. And so we're now integrating over flat connections. The flat connections include these wiggly boundaries. And there's a measure on the flat connections that you get from the BF theory, the Weil-Petersen measure. And that measure is the measure associated to the symplectic form here. So that's a direct way of showing that the measure in JT gravity gives you the symplectic measure for the space diff S1 mod SL2R.
I remember the APL transcendental gravity theory is not extended to classical Einstein gravity. It's not extended as a test integral of Einstein gravity theory. It accompanied.
Well, in this case, in this case, it is the same. Now, there are subtleties in that you have to say exactly which types of connections you're going to integrate over. But we can restrict to the flat connections that correspond to those wiggly boundaries. Those are the ones that are relevant from the interpretation in terms of gravity or the Schwarzian theory. And the measure is the symplectic measure. Okay, so anyhow, this shows that the Schwarzian theory is one loop exact. So we can write an exact expression for this partition function. And what we got from a discussion before, we just computed the classical version by plugging in the saddle point in here. And the classical expression was e to the n s naught plus something like this. I'm not sure of the exact factors, but they're not important. Now we need to include the one-loop determinant. And since I'm a little short on time, I'm not going to go through the calculation of the one-loop determinant, but it's an easy calculation. And you get 1 over, some constant that's not determined by the measure. There's an ambiguous constant that can be absorbed into this factor here, times 1 over beta j to the power 3/2. Okay. So this is the exact path integral of the Schwarzian theory. Yeah?
So is it surprising that it's
well, yeah, it was.
or is it obvious that it's
No, it wasn't obvious. Actually, as I'll comment in a second, this factor here is visible in the numerics. So you can see this 1 over t cubed behavior. And we were puzzled by this for a while because that was the one loop answer, but the numerics, it seemed like it was the exact answer. So it was a case where a one loop exact path integral was sort of discovered by numerics, which is not a good way to discover it.
after you guys there was
was the people who did a change of variable with Gaussianized.
Yes.
Is that valid?
Yeah, the tricky thing in that change of variables is accounting for the SL2R redundancy, so integrating over diff S1 mod SL2R instead of diff S1. And I don't understand a very clear way of doing that in those terms, but it could be that that makes sense. Yeah, I should mention that there have been many. One of the interesting things about this Shortsian theory is that there are many different ways of calculating this partition function, and they're really different. So there's one way which is based on this Storch-Zermatt-Heckman theorem. There's another way which is based on thinking either about the quantum mechanics problem that we have here, and basically just diagonalizing the Hamiltonian of that quantum mechanics problem. You can do that either by thinking of this as a type of Liouville theory in one dimension, like Liouville quantum mechanics, or you can do it by thinking about the particle in a magnetic field picture that we discussed yesterday for the JT gravity. But there are other ways, like there's a way of starting from two-dimensional Liouville theory and taking a limit where the q parameter e to the minus tau goes to 1 and c goes to infinity with q to the c held fixed. Then you get this function. And there's another way which is even more different, where you take a double-scaled limit of the SYK model, and then you analyze the partition function of that theory exactly in the double-scaled limit, and then go to low energies, and you find this. And the methods involved in these different computations are really very different from each other. So it's sort of interesting that there are so many different ways of computing this answer. Been done by many different groups of people. So, yeah.
So in this partition approach, you took what are the fixed points?
Sorry?
Circle, what are the fixed points?
Oh yeah, the fixed point, it's just the saddle point that we discussed before, where phi is constant. So that's the saddle point. There's just one saddle point up to the SL2R, which we're quotienting by, and then there's a single saddle point, and the fluctuations about it, they give this factor. Yeah.
Yesterday you alluded to a particle in an electric field, but this time you said magnetic field.
Oh yeah, that's sort of a matter of taste. So okay. So anyhow, now we have an exact expression for the partition function in JT gravity, and we can compute. Okay, so now let's start doing a naive computation. Z of beta plus IT, Z of beta minus IT. Well, we just take these two calculations separately, and we get the square of this answer, which will behave for large times like e to the 2n s naught divided by t cubed. I should have written an arrow here or something to represent that we're taking time to be large. So this actually reproduces the slope region of the plot of the SYK model. And we get the same power as we got in the case of a random matrix. That's not essential. That isn't a prediction of random matrix universality. That's sort of a coincidence. But its explanation comes from the same place as in random matrix theory, which is that the density of eigenvalues in the SYK model vanishes like a square root. So we can take this expression for the partition function and try to write it as an integral with some density of eigenvalues of e to the minus beta lambda. And you can compute this function rho naught of lambda by doing an inverse Laplace transform of this expression. And you find rho naught of lambda is e to the n s naught times sinh of some number times square root of e. So for e near 0, this thing vanishes like a square root, just like for the GUE ensemble. What I'm saying is that it's not a consequence of random matrix universality. So there are other SYK models that will have the same type of random matrix statistics that have different behavior near the edge. Like, for example, this supersymmetric SYK models. They have either, well, for example, the n equals 1 supersymmetric SYK model has 1 over square root of energy behavior near the edge of the spectrum. But the statistics in the bulk are, again, the same type of random matrix ensembles. Okay, so how much of the spectral form factor curve have we explained so far? Not very much. Just the slope region, the initial slope region. We need to do better than that. Now, a hint about how to go further is to use the fact that in the ramp region and the plateau region, this spectral form factor is not self-averaging. So what that means is that the expectation value of z times z star is different from the expectation value of z times the expectation value of z star. And what we're computing here is really just the expectation value of z. So we need somehow an effect where expectation value of z times z star is different. And in the SYK model, it's easy to see how this can happen. In order to compute the disorder average of z times z star in the SYK model, in principle, we should use two replicas of the SYK model. And we should do the disorder average to the product of their partition functions. The two replicas we can represent in a collective field representation in terms of G and sigma fields, bilocal G and sigma fields, like we did for a single copy of the SYK model. There will be more G and sigma variables, because we'll need a G variable that describes a bilinear in the fermions, where one fermion is in one copy and the other fermion is in the other copy. And a way to get a non-self-averaging contribution is to consider what's called a replica non-diagonal saddle point, where the collective field that involves a fermion on one system and the other system has a non-zero value. So that's a configuration in the G and sigma space that only makes sense if you have two copies. If you have two copies, you're considering a two-replica quantity. And a contribution of that type will give something which is manifestly not self-averaging. It will be a contribution to the expectation value of z star that would not be present for just z or z star alone. Now, what this type of configuration represents is it represents a correlation between the two copies of the partition function. And you can write down solutions to the saddle point equations of two SYK models and analyze them and find this slope region of the curve. What we're going to do is discuss only a simple version of that for JT gravity, which is an accurate representation of the saddle point of the SYK model at low temperature. And it's much easier to draw the pictures. Yes?
You just said slope. Did you mean ramp?
Yeah, I meant ramp. Sorry. Yeah, thank you. This replica non-diagonal saddle point in the SYK model, correlating the two replicas together, gives you the ramp contribution. And we're going to discuss what that saddle point looks like in JT gravity variables. Yeah.
But you need access to exponentially large in n times, right?
Yeah, that's right. So, well, in other words, what happens is this contribution is very small at early times, and it only becomes significant at exponentially large times, where this contribution has become tiny. Sorry? Yes, you can. I mean, in the semi-classical integral, e to the minus n times some action, you can calculate, it's basically just a non-trivial saddle point. So it's exponentially smaller in n than the original saddle point, but it's growing in time, whereas this one is decaying in time, so at very large times it will be relevant. We'll write formulas that have this property, and you'll see in more detail. So I'm running short on time, and I'm basically going to run out of time, so I'll have to continue the calculation tomorrow. But let me just sketch for you what configuration we're going to be looking at in JT gravity. So when we introduced JT gravity, we described the boundary conditions that are relevant for computing the thermal partition function. It involved taking a manifold with a boundary that had length that was beta over epsilon. And if we're trying to compute a quantity, let's forget about this analytically continued quantity for a second and think just about two copies of the Euclidean partition function, z of beta times z of beta 1 times z of beta 2. So now we need a manifold that has two boundaries, one with length proportional to beta 1 and one with length proportional to beta 2. And the classical solution that we're using here corresponds to a disconnected manifold, where we have two of these hyperbolic disks, and we have a wiggly boundary with length proportional to beta 1 And we have a second wiggly disk, a second disk with a wiggly boundary with length proportional to beta 2. Okay. But we can imagine another type of manifold that has two boundaries like this. Which is the following. Take something like this, and then we can put our one wiggly boundary over here and one wiggly boundary over here. This one will have length proportional to beta 1, and this will have length proportional to beta 2. And now the manifold we take is the thing in between these two boundaries. And at least qualitatively, this seems to be on the right track, because this is a configuration that makes sense if we have two replicas, but wouldn't make sense if we had one. And it describes a correlation between the two partition functions we have, z of beta 1 and z of beta 2. How much time do I have left?
4 minutes.
Okay. Let me think if I actually want to begin doing this calculation now. Maybe I'd better just leave the calculation so I don't stop halfway through it. We'll leave the calculation for the beginning of tomorrow morning, and I'll stop a couple minutes early now and see if there are any questions. Thanks. Yeah.
SYK matrix model. And the question is, what does SYK teach us about aspects of quantum gravity beyond what we learned from matrix model?
Well, I guess one thing is that it wasn't very clear how to describe black holes in the. You're talking about the matrix integrals, like the s equals 0, s equals 1, or the minimal string matrix. Yeah. So it wasn't very clear how to describe black holes in those cases. And SYK is a nice theory in the sense that it's sort of at least a qualitatively good representation of a black hole. And the correspondence is even a little bit more precise through this JT gravity. So that's an advantage of this setting.
So what did we learn about the black holes in the context of quantum gravity?
Okay, well, that's really going to be the subject of discussion tomorrow, and we're not done. And certainly, honestly, at this point, I'm sort of confused, as you'll see tomorrow. But yeah. Yeah.
Can you explain a little more this Yang Coulomb propulsion from the log term in the vandermonde method?
Yeah, well, that's just the potential that you would get for a Coulomb interaction in one dimension. So you can think of this term where the eigenvalues, you can think of this potential for the eigenvalues as a statistical mechanics problem for a bunch of charges sitting in some external potential, which is given by V, and also having the logarithmic potential from the Coulomb interactions in one dimension.
Yes, I'm confused because I feel like the potential is usually 1 over r in 4 dimensions, and then in 1 dimension it's only become log. Is there something I'm missing?
It's 1 over r squared.
1 over r is 0. Yeah, that's well, anyway.
Are there any other questions? Yeah.
So you calculated this order correlation function thing, and you get an average in the matrix model, right? You average over the possible over the example, right? We did.
Sorry, could you say it again?
Yeah. So you wrote down the position function.
Yes.
Two copies them, and you took an average. That was in the part of the matrix.
Yes.
Right?
Yes.
And now when you're doing it for the related gravity, what is the equivalent of taking the average?
Oh, yeah, this is a great question, and I don't have an answer to it from the perspective of gravity. From the perspective of SYK, the thing that's being averaged are the couplings. And so it looks like what well, this question will be more reasonable tomorrow, but it looks like JT gravity wants to describe an ensemble average of theories, not a single theory. And that's somewhat weird concept from the perspective of gravity, but it seems to be the case for at least this gravity theory. Yeah, well, I might say more about this tomorrow. Certainly your question will be more relevant tomorrow.
There will be a change in little change in the program. We will regather at 11:20 instead of 11:30. And let's thank now.